All right, where do I start here? All right, so guys probably know this is my first workshop I've given, and so in the not so unlikely chance that I bollocks this entire thing up, I apologise in advance, but I'll see what I can do. Okay, so I'll try and make this as interactive and sort of. I'm not trying to give a lecture on mathematical cryptography or anything. What I'm aiming to do is give a kind of crash course on practical cryptography, and show you what kind of challenges you might see in a CTF relating to cryptography, show you some basic tools and techniques for finishing those challenges. And so I'd appreciate if anyone, if they want to speak up or ask any questions, or I don't know, just just talk in chat or unmute your mic if you want to say anything. Right, so I'll start with some, definitions and terminology, obviously. So cryptography is the area of research around ciphers, and a cipher is just a set of algorithms for encryption and decryption. So the terminology basically, if you got a function encryption E that takes a message, also known as a plain text, and a key K. That's the either the private key or the secret key, depending on where it's being used. You get the C, which is the ciphertext, and that's the terminology that's used the majority of the time. Now, note that by definition, if this key here is not included, then it is not encryption, but something else. Because you might often see, if you read the right textbooks or the wrong textbooks rather, you might at some point see something like this come up, asking you to encrypt something using base 64, which is definitionally not encryption. However, base 64 does obviously come up a lot because it's a convenient way to encode things. So. And you can tell, the equal sign at the end for padding. That's a common way to tell that something's base 64. Some CTFs will often just give you the flag in base 64 and call that crypto. I think AU CTF did that earlier this semester. What now? Now we can probably get started on an actual simple form of cryptography, and the simplest form has got to be something known as a Caeser cipher. A Caeser cipher is just also sometimes called a shift cipher or something similar. It basically maps a series of inputs in the plain text, one character or one chunk of characters at a time, into an output. So if you've got the characters A, B, C, D, so on, it might map to D, E, F, and so forth. Now, let me check. For example, this is something that you might see at some point. Now, this is very clearly some kind of substitution cipher. You can tell here with the capital letters and this, that's in flag format somewhere. I'll put that in the chat if anyone wants to have a look at it. But now you just need to do some cryptanalysis to try and figure out how to decode it. And the simplest way to do that would be to, because there's only 25 different ways or 26 ways that you can do something like this. Simplest way is to try all combinations of it. And so if you've got a plain text here, if you've got a ciphertext here and you want to figure out how to decode it, you can just try all possible combinations of it until you get something that looks decent. So you can see MonSec Caeser ciphers are not very strong. Some people and a Caeser cipher can be shifted really any number of ways. But that being said, a Caeser cipher does not. There are other substitution ciphers that don't just shift characters some way, and the simplest form. So the other sort of form of substitution cipher you see come up is either. I'll start again. Substitution ciphers are always going to be either monoalphabetic or polyalphabetic, and a monoalphabetic one means that it just basically means there's a one-to-one correlation, a one-to-one mapping between the input and the output. So even if you've got one that isn't just a simple shift, if you've got A maps to Y, B maps to F, whatever, there are still different ways that you can decrypt these by doing some simple methods. Hang on, here's the next one that I'll take a look at. Here you can see that, you can see, there's some spacing, punctuation, so you can get some general clues as to how this works already. I'll put this in chat if anyone wants to have a look at it. But the first tool that you can do is do some simple language analysis. And the way to do that is to look at, which characters are the most common, which pairs of characters are the most common. And let me check. The simplest way is just to look at which one is, what I got here. So here you can see that obviously the space character is the most common. That's not really very interesting to us. But here we also see that the letter M and the letter I are the two most common letters. Now in natural English language, in most situations, the letter E is the most common, followed by the letter T and so on and so forth. And so we can reasonably assume that the letter M or the letter I either maps to E. So we can figure some of this out. Now here, now in this thing here, let me check. Sorry. Based on the way this comes up, you can probably tell that M is the most likely one to. M is probably the most likely one to map to E, and there are tools online that you can use to break these. So what can we do first? Well, first we know that that M is probably the most likely map to E, so we can replace that there. What else? And from, what else? What have I got written down here? And we also know that now there aren't that many words there aren't that many two-letter words that end with E, and this word comes up, the exact same word comes up twice, and so we can probably tell, well, this letter likely maps to the letter W. What else? And we also see what comes up more.
Would the apostrophe P in the top row be indicate that P is S?
Oh yeah, that's a good point. We can also tell that maps to there. What else? We also see the letter, so we also see the phrase, we also see this come up. Maybe you might be able to tell that this letter, the word own. And you might, at this point, you might be able to start telling what this phrase is. The phrase whim comes up a fair bit, last letter E, so this might be, R. And here you can start to fill in the blanks. So this is this is just some phrase I found on the front of the MonSec website. X maps to U. You can tell this means university. And you can keep doing this to finish it. But in practice, in a CTF, the easiest way to do this is just to click the auto solve button, which will just go through, try a whole bunch of things, do some statistical magic, and work it out for you. This is taking a bit long. Yep, there we go. We are MonSec, we are Monash University's very own cybersecurity club. Yep. Now, there are lots of different forms of these. Some of them sound more complicated than others. For example, there's a form, in the AU CTF early last semester, there was something called an affine cipher or an affine cipher, I can't remember how to pronounce it, where it would map each word to a letter, to a number, do some kind of linear transformation, reduce it over a modulo, and just do all these things with maths. But fundamentally, it was just a one-to-one character mapping that was the same every time, and so it could be broken with the exact same tricks. Now, these are very simple and easy to break, given enough information. But the other form of substitution cipher you see come up a lot is something called a polyalphabetic substitution cipher. which just means many alphabets. When this happens, you can't make any kind of guarantee that the same letter will map to the same output letter. The version of this comes up the most is called a Vignere cipher. And what a Vignere cipher does is you select a smaller key instead of an entire alphabet, repeat that key. So let's say we want to encrypt the phrase, hello world. And we want to use the key, just the word key, because we're being original here. And it's as simple as you map here, and then you just simply repeat it. Now, what a Vignere cipher does next is it assigns a number for each unique character. For example, A starts at 0, then B is 2, C is 3, so on. Now here we know that K, following that pattern, K is 10, H equals 7, and so 10 plus 7, 10 plus 7 is just 17, which is letter 1. And following on this pattern, you just get R, I, J, V, S, U, Y, V, J, N. Now, the most important thing here to keep in mind is that because the key is repeating and because you're using a repeating key rather than just a single substitution alphabet, the same letter here, the word L, the letter L comes up twice, but it maps to 2 different characters. And so you have to be more creative with the sort of analysis you do. And the example I'll show for this is also from AUCTF. Where's this? In AUCTF, we were given this giant chunk of text here, and for some basic analysis, we're able to figure out that it's a Vignere cipher. And even though we can't uniquely look at the text and say, well, this letter comes up the most, so it's probably an E, then it's T, so forth. And but you still definitely see there are patterns here. And once again, the solution to this, actually, hang on, I'll put this. I've got a link here. I'll put in chat if anyone wants to have a go at this. But once again, the solution that ended up working was just. Where have I got? Did I actually do this? If you just Google the best version that I found was from this website, which has a series of other similar solvers. Obviously, change language to English, and you paste the text, context, and if you click break cipher, it'll do some work on itself. It'll do some work on it. And this isn't perfect. This is clearly not the solution we're looking for, but we can see the phrase in at manager, something that looks like the word vulnerable almost. That's probably the word father. So we're getting close, but we need to muck around with it a bit more. So if we change the key length up to 35, it'll have another go at it. And back during the CTF, I spent longer on this than I'm willing to admit before someone else jumped in and upped the key length to a substantial amount. Still doesn't work, so we'll change it to 40. And yep, that works. That looks better. That looks better. In my younger and more vulnerable years, whatever, and at some point they mention what the flag is. And that was what the solution was in the end. What else? Yeah, and there are lots of different types of polyalphabetic substitution ciphers. For example, the German Enigma was technically a polyalphabetic substitution cipher because it was simply taking in one character at a time, doing some magic on them, and spitting out one character at a time where each character had been mapped to something else. But the difficulty with it was that the same character pressed multiple times would obviously map to different outputs. Now, to move on from here, we need to cover another topic which comes up a lot in cryptography, which is the idea of the XOR Boolean function. Now, XOR is often denoted with this symbol. If you've done MAT 1830 or FIT 1047, you might have seen this. What this does is it simply takes in 2 bits and returns an output bit. So if you've got 2 bits, A and B, and you've got the output A XOR B. An input of 0 and 0 is 0, 0, 1 is 1, 1 and 0 is 1, and 1, 1 is 0. Now there are lots of different ways of thinking about it. Some people call it binary addition because 0 plus 0 is 0, 1 plus 0 is 1, but 1 plus 1 is 0 because you can imagine that it would overflow, and we're ignoring overflows in this bit, in this case. Or another way you could think of it is basically the output is 1 or 0 depending on if the inputs are different. Now, the main thing that XOR comes up for in cryptography is the main application of XOR in cryptography is through something called one-time pads, also known as Van ciphers. So basically, a one-time pad simply takes in. So you've got the encryption function I mentioned earlier, E of M, K. You simply get the inputs and both the inputs and just XOR them together. M, XOR, K. And you're probably thinking, what if I want to encrypt more than 1 bit at a time? And the way you do that is that you just have to represent the number in question in binary and do all the bitwise operators on each bit separately. So let's say, for example, we want to compute. So let's say we want to compute 5 XOR 7. Well, we just simply break this into binary. So 5 XOR 7 in base 2 is 1, 0, 1 XOR 1, 1, 1. And 1 XOR 1 is 0, 0 XOR 1 is 1, 1 XOR 1 is 0. And so the output of this is 2. So we can just say 5 XOR 7 equals 2. So using the same terminology we used before, the message is 5, the key is 7, and the ciphertext is the number 2. And then simply to get the resulting message back, you simply XOR the key. So to decrypt it, you simply get the ciphertext K and just XOR them together again. And so I'm looking at another screen when I'm writing this, so tell me if I write off the side and you can't see anything. Now, the reason this works is that there's a couple of interesting properties that XOR has. So, for example, anything XORed with itself is 0. So A XOR A equals 0. And the way it happened before, and the reason is because, using the analogy I made before, the output of XOR is 1 or 0 depending on if the bits are different. And so you can tell intuitively that the same input, the same number XORed with itself will always result in a 0. And additionally, for similar reasons, anything XORed with just a 0 will always be itself. And the reason this cipher works is because you can imagine that when you encrypt a message with the key K, you get the ciphertext. And to get this back, you simply XOR the ciphertext with the key. This is the same as just doing M XOR K XOR K. And obviously, as we covered, anything XORed with itself is 0, so this is just M XOR 0, which is just equal to M. And so it doesn't seem too complicated. Now, the reason that this cipher is so common, that this cipher is so useful, is that technically speaking, if you use it right and you adhere to 3 important guidelines, it can be theoretically and absolutely unbreakable under any circumstances. Although obviously, for reasons I'll cover in a second, those circumstances almost never occur in practice. the first main issue, and this is probably the biggest limiting factor. The message, the plain text and the key must be the same length. Sorry if my handwriting is illegible. And so this is probably the biggest limiting factor of pure one-time pads, because you can intuitively tell that if you encrypt a message and you send an encrypted message to someone, you need a way to send the key to them. And if you've already got a way to send a key of the same length as a message to someone, then you can just use that method to send the message without bothering with encryption. What else? Hang on. And also the key must not be reused. So all keys K must be unique. And it must also be unpredictable. Yeah, I'm sorry, that's pretty illegible. But now the first thing that you might come across is that one thing that you might see a lot is the key not being the same length. So that you might see the key not being the same length as the message. And here's a good example of this you might see. Obviously, it's encoded in base 64 because that's a notation that's easier to. It's just a convenient way to notate different things. And so obviously, because the key length isn't the same as the message length, you can just brute force different ones. And so the way you do this, sorry, I'll put this in chat if anyone wants to have a go at it. But the way you'd have a go at this is by first decoding from base 64. And then CyberChef. So CyberChef's a very useful tool in crypto. It comes up a lot. So it's probably completed a lot of challenges for me over the last semester. And now there's a tool called XOR Brute Force, which will just try a whole bunch of things for you. Now here it's just going through and XORing this with a whole bunch of different keys of 1 byte length to see, and you can just go through and see which ones look legible. But let's say that we know that this is encoded so that the message in here has the standard flag format. So we can say, well, let's filter out the ones that don't contain the string of MonSec. And here we've got another flag, MonSec, beware of short keys. Yep. Now, the next issue we had was that all K must be unique. And the reason is that the reason that these are called one-time pads is because all the keys must be used at most at one time. And I'll just quickly show you why that's the case. If you've got two messages, M1 XOR K and M2 XOR K, this is the exact same K in both cases. If you XOR both of these ciphertexts together, the result you'll get is M1 XOR M2 XOR K XOR K. And obviously these Ks will just cancel out and you're left with the messages XOR together. Now there's no perfect way to get these back. Once again, it's just more statistical magic and trial and error. However, you can tell that there are going to be interesting patterns that you can look for and abuse. Like this answer in Stack Overflow, I think, gives a pretty good analysis of it. Let's say that you got the message here represented as a black and white image for each 1 and 0. The message here is send cache, and you XOR it with this piece of very random information. So clearly, the other considerations are kept in mind where the message has to be random, and you get this ciphertext which is completely random. But then let's say you encrypt this smiley face using the exact same message, you get this, which on its own again is impossible to reverse. But then if you XOR both of the resulting ciphertexts together, then what you get is this. And I mean, there's no perfect way to get the image back from it. Obviously, it depends on what you know about the image, but you can see here that there's some very obvious you can tell here that there's some very obvious patterns. Now here's a challenge that might come up. What is this? Let me just get this up. So let's say, now this is a very common format for a crypto challenge where they give you the source code of a challenge and the resulting output, but obviously they hide the flag and don't tell you what the flag is. So here you've got this just defines a function which XORs bytes together because that's just more convenient for some uses. M1 is imported from here, which is hidden and you're not given, so you have no information about one message. However, you're given this second message, or at least part of it. You know that one of the messages says, congrats, the flag is something. You don't know what the flag is, and you don't know what this message is. And hang on, where's the output? And the result from this is to get two ciphertexts here encoded in hex. Now, the way to break this is using a process called crib dragging. And crib dragging is basically making a guess as to what one of the messages entails. So you can imagine if you've got, check, where's this? So let's say, once again, you've got this resulting message here. Now this message is just M1 XOR M2, which is what we get if we XOR those other bytes, those other hex strings together. And what we can do is, if we know or can reasonably guess part of the message, we can get a small string of text which we think might exist somewhere and XOR that with a small section of it. And then if we, the reason this works is if we've got M1 XOR M2, and let's say we want to make a guess as to what, so let's say we know a little bit of information about M1. We can just XOR that with M1, with a bit of information we get. So with M1, and these will cancel out, and you're left with M2. And from that guess, you can tell that if M2 seems legible or reasonable, you can correctly assume that that is probably what the part of the message is. And then you use that bit of information to make more guesses as to the format of the other one, and so forth, and just keep going for a while. The way you do this in practice is to use, there are some very useful tools that will do lots of crib dragging for you. This is the best website that I was able to find. Let's say we get one message, one ciphertext here. This is ciphertext 1, which is this is the one we have no idea what's in it. But the ciphertext 2 is this. Now we can go here, we can, like one common guess would be to just do space, and it'll go through, grab crib and look for all these different things. It's automatically highlighting the ones that it thinks seem more than somewhat reasonable. I don't know, the word here seems okay. But in our case, we've got a bit more information than that because we know the format of one of the messages. We know that it says, congrats, the flag is MonSec something. And so we can try dragging that piece of partial plain text with it. So if we say, and you can start to see a message here forming. All the other ones seem pretty unreasonable, but this one is not a bad guess. I think that's capital. So if you say that, okay, we can assume that this is part of message 1, put that in. You can see a very obvious pattern, and you probably know that this string is going to be the quick brown fox jumped over the lazy dog. If you go through here, then you can see one of the other strings from here that seems to appear. You can put that in here, and then we get the other, the next flag. Now, the final piece of, the final way that you can break XOR ciphers is by predicting, is by breaking randomness. Is by predicting the randomness. Now, obviously, in practice, because of one-time pads limitations, almost nobody uses them purely. Instead, what they use is they use instead of XORing the message with the key, they instead XOR the message with a pseudo-random number generator. It's called G, the key. And the way this works is G is a random number generator which you seed with a value K, and because it's purely deterministic, if you give it the same seed, it will be able to, if you give it the same seed, it will be able to, it will end up giving the exact same output. And so you can encrypt this message, send it to someone, but instead of giving them the entire pad that was used to it, you just send them a single key, which was used to seed the piece of information. And breaking these is where cryptography starts to get interesting. So let's say that we've got a once again, using the same format, let's say that we've got this challenge here. And can anyone, see anything immediately glaring to them? Because here it's, sorry, go on. So am I going a bit fast also?
No, you're fine.
Yeah, whatever.
But also, first thing that jumps out to me, you're using the same message from before. Come on, man. Be unique.
Sorry, I think I put this all together in the span of 20 minutes, so I think they're all pretty similar. I mean, obviously the messages can be different between challenges, so I'm just trying to introduce topics. Yeah. Does anyone see any glaring issues with this? Any way?
You're seeding with the time.
Yeah, so. Exactly. Yeah. Now this comes up an awful lot. Like this should immediately start. This should be. This looks very wrong, but it does come up a lot. And the way this would typically work in a CTF is that you can, like for example, the way I see it often is that you'll be given a netcat session which will give you access to a script which will encrypt a piece of information for you. But because you know roughly when it was encrypted, you can reasonably figure out what the key is and just try a couple of things. But even if that's not the case, I'm going to show you how you can still break that in a worse situation. And what have I got here? Oh, sorry, I probably should show you the output. And the output of this is just a byte string because what it's doing is it's generating a key. It's seeding what it's doing is it's seeding random using the system time, generating a random key, and XORing that key with the ciphertext. And then it's just printing that ciphertext out. And so what we can do is, because we know we've got to be a valid time, we can just try a whole bunch of them. So what's my solution here? Obviously, the first bit is just to define, put the thing in here, and I'll move over the same function I had from before, just because I'm going to be XORing a bit. But then we can just I'll save the time of typing this all out live. But what this function here does is a checking function. What it does, it takes in a seed, we'll seed it with that value, generate. It will also, once again, because we know the message format here, for the same reason that we were able to do the cryptdragging in the last challenge, we know that if we XOR the first 9 characters of the ciphertext with the string congrats, we will get the first 9 bytes of information that were produced by this line here, which is why I'm using for range 9. Oh. Yeah, thanks, Daniel. But, now, we don't actually need to know when this is encrypted. Obviously, it's quicker. But what we can just do is, for I in range... Sorry, I better import time first. Let's copy this over to save some more time. Now, what this does is, for I in range into time.time minus this is just how many seconds there are in 2 days. And so I'm just assuming reasonably that I know this message was encrypted sometime in the last 2 days. you could do in the last 2 years, but that would just take a bit longer. And then you just do if check I print I. Now we run that. Oh, sorry, I didn't import random. Oh, that's right, yeah. Sorry, I should have explained this earlier, but output is the, I'm just using byte XOR on the first 9 characters of the ciphertext and the first 9 characters that we know. Because we know if we XOR these together, we will get the bits of information produced by random. So if we just run this again, hopefully didn't forget anything else. No, I didn't copy the wrong piece. That'll run for a bit. And if I'm lucky, yep, so there we go, that we know. From that, we know that is what the system time was when this was encrypted. And so if we seed with this, then we will get to the same state that the system was in when it was encrypted. And so we can produce new key is, and then you just and then we just do random.randint with the same setup that they used with the same key. And then hopefully, if we just do a byte XOR, then we will get the new flag. Your flag is MonSec. Don't seed don't seed random with time, which is a pretty reasonable suggestion. What next?
Sorry, really quickly, where did you get that check function from?
Oh, sorry. I'll just. When did I get this? So it's nothing fancy. I just wrote this myself. What it does is you take in, all it's doing is it's taking in a seed, seeding with that piece of random information, producing a bit of, producing 9 bytes. And if that 9 bytes is equal to the 9 bytes we want, then we know that we found the seed. And otherwise we just return false. And so that's just a helper function, so we can brute force a whole bunch of seeds. Yeah. Does anyone else have any questions?
Yeah, I just have a question going back to the end when you add in a new key, when you're trying to generate, if you go back to your terminal.
Yeah. So I'll just copy the whole script in here.
Yeah,
Just
no worries. Okay.
Yeah.
So yeah, new key. So new key, is it going to always be the same, or because aren't you doing like random using?
Yes. Well, once it is always going to be the same because we are seeding it with a fixed value.
Oh, okay. Yeah. I saw you did up there.
Yeah.
Okay, gotcha.
Yeah. So for example, if we let's say we do random.seed with just the number 5 random. Those are the first 4 values, and it's going to keep producing more random values. But even if I close this, run another thing, import random. As you can see, this is the exact same number both times because we seeded it with the value that we wanted in the first place. So this is mainly a tool for, I know it's quite a useful tool for developing, just because if you want something random, but for the purpose of developing, you want it to be kind of predictable, you can just set it to a fixed value so the data is the same each time. Yeah.
Cool.
Has anyone else got any questions? No, we'll keep going then. I might just make a proper file for this just because. So the next next topic I'm going to cover is just some basic RSA. Now, has anyone here not really familiar with RSA? Heard of it? Know the concepts? Or I'll just start from scratch. All right. So do people here know what public key cryptography is? However, so basically,
vaguely.
Sorry, go on.
Vaguely remember from 1047.
All right, yeah. So basically, so crypto is either symmetric or asymmetric. Now, symmetric is just everything we've covered up until now. You've got a function encrypt with the key, and you decrypt with the key. But asymmetric or public key cryptography, you're given a public key and a private key. And so the public key in RSA is a set of two numbers called E and N. Here, E is sometimes called the public exponent and N is called the modulus. And private is the numbers D and N. And so the way it works is, if you want to encrypt a piece of information, you use the public key, but the private key is used for decrypting. And this comes up a lot. For example, if you're having a conversation over a network that you know is being monitored, you can't just encrypt a message and send the key over the network because someone's going to pick up the key. But if someone instead sends you their public key, you encrypt with the public key, then send that back to them, nobody will be able to decrypt it because the private key stayed with them. So let me check. Now, the way this works is that in RSA, there are two main functions. To encrypt a message using someone's key, kpub, or this is just equal to the message or the plain text raised to the power of the public exponents, or E, and then reduced modulo N. And N is basically, sorry, do people know what modulus means?
Yep.
The remainder.
Yeah. Or another way to think of it is, you know, like for example, on a clock, times are calculated modulo 12, which means that if someone says, can you meet me at the cafe at 13 o'clock, if they're from Europe or something, then you know that means 1 o'clock because there's a remainder of 1. And to decrypt, with RSA, well, it's you just get the ciphertext and raise to the power of D modulo N again. Now E is a constant standard. Like, people often use 3, 13, but the most common is 65,537, which is just 2 to the power of 16 plus 1. N, hang on. Just trying to. Sorry, it's a bit hard to. I've got a different screen here that sees different things. And N, or the modulus, is a large number, typically at least 1024 bits, which is the product of two prime numbers called P and Q. And D is the interesting one, though. D is equal to, there are different ways of notating it, but it's often called the modular multiplicative inverse of E modulo something called phi, can't really draw that, of N. Now, phi of N is essentially just P minus 1 times Q minus 1. And so, but the reason this is so secure is that to encrypt, you only need to know E and N, but to decrypt, you need to know D. And to know D, you need to know what P and Q are. And so that means that the security in RSA relies on the fact that it's very difficult to find the prime factors of a large number. And so we'll start with a simple RSA challenge. What have I got here? This is a common format used in RSA, in crypto challenges. Let's say we've got this input here. We've got a modulus N, E, and we've got a ciphertext C. Can anyone think of how they'd go about decrypting this? Anyone? Well, to decrypt it, obviously, as we covered as we covered before, we need to know the values of P and Q. And what are they? They are the prime factors. But I thought, no, and we did just mention that the prime factors are very hard to calculate. But the issue here is that this number, it might look big, but in terms of cryptography, it's very small. In fact, this number is only 200 or so bits, which is absolutely nothing. And so so in RSA, when you get an RSA challenge, the first thing you should always do is check FactorDB. And FactorDB just calculates and has lots of lots of numbers, prime factors listed. So if you go into here, try to factorize, it'll tell you what the two factors are. And so the way you decrypt this is by, obviously you say what P and Q are. So let's say P equals this, Q equals this. The first thing you should do is import a function. This just imports a lot of functions that come in handy. If you want to install this, you have to do pip install pycrypto or pycryptodome, and it's very handy, so it's worth having. And once again, as we covered here, phi is equal to P minus 1 times Q minus 1. So the first thing you do is to say phi is equal to P minus 1 times Q minus 1. We already know E, but D is a bit more interesting. D is now crypto util number, it's got a function in it called inverse, which just does this automatically. In practice, you'd want to use the extended Euclidean algorithm or use some other formula to figure it out. But you can just say D equals inverse of E and phi. Now, if we just try running this, hang on. Yep, we didn't get any errors, but I haven't printed anything yet. So now we just need to, so now we've figured out the private exponent, which means we should be able to decrypt this. And once again, the formula for that is, so the formula is that if the ciphertext is the power of D mod n, n is equal to m. And that's what we're looking for. So you can just do that using Python's built-in power function. So you can just say, keeping that inside. So you can say m equals power c, d, and n, which raises m to the power, which raises c to the power of d and reduces it modulo n. And now we can just print m. You might be wondering what the output this is, and we just get this number. And it might not seem obvious how you get the flag from here. Perhaps if I were to print this in hex, it would seem a bit more clear. And 4D, 4F, I mean, this looks sort of like hexadecimal characters, because we know that hex 4D is the character M. And so you'd have to go through here and calculate the characters, the ASCII values. But the interesting thing is that crypto util number, it has a function that does this automatically for you, so you don't have to plug into CyberChef or whatever. So you can just say, instead of printing just the number, you can say print long 2 bytes M. So, and there we go, we got the flag. MonSec RSA isn't too bad. So let me check. What's my next challenge? Now this is another interesting one. So this is so I've got this other challenge here. Now once again this modulus seems quite big, and so it definitely isn't going to be. Actually no. Oh no, sorry, that's wrong. I think it's a fairly sizable modulus, but that in itself doesn't mean that you can't factor it. So once again, the first step So it's 1024-bit. Once again, the first step is always to check factor DB and factorize it. And the result should be, now that looks pretty scary. I'm not really sure what there is to think there. Can anyone think of how they go about solving this?
First off, what are we actually looking at?
So this is a list of factors. So hang on. So n. Sorry, I could have explained this a bit better. But n is n is equal to p times q typically. But this is a strange question, and I see a lot of crypto challenges where they try and tweak the parameters and make them really strange, and so you have to do a bit more looking into it. But in this case, we've got what looks like dozens of factors, and so in this case, n is equal to a times b times c times d times e, so on. And so once again, hang on. The only thing that's different here comes down to how you calculate phi. So usually in this setting, phi would equal p minus 1 times q minus 1. But one other interesting thing is that technically you can just keep going. You can say p minus 1 times q minus 1 times r minus 1 and so forth. And the way you do this is by, once again, using Python, because that's a lot simpler than doing this all by hand. And so we just copy all the parameters over here. Now, technically, you could go to FactorDB and just copy these all by hand, but that is an absolute pain. And so what's more useful to use is something called the FactorDB API. And so if we just copy the, sorry, I think I might have copied the wrong numbers there. Is this right? Actually, yeah, sorry, I had the wrong numbers before, but everything I set up until that point was still right. And so what we want to do here is we want to copy the number, run it through FactorDB API. So we want JSON because it's easier to read, and copy the number in. And it'll return this big list. We can just copy the list of factors here. And so we get this. And once again, we're trying to calculate, p minus 1 times q minus 1 times r minus 1, so on, and for all the numbers. So you just do this by setting phi initially to 1. And you'd say for I in factors, you just want to say phi times equals I minus 1. And that would just calculate phi for you. After that, you just do the exact same steps. So d equals inverse a phi m equals c to the power of d mod n. Then we just print that number out in bytes, long 2 bytes m. Now, fingers crossed, if I run this now, we'll get, yep, there's the flag, MonSec, lots of factors are fun. Does anyone have any questions?
How do you end up finding things like FactorDB?
FactorDB is very useful. It's I'm not sure. I can't honestly remember. Like, hang on. I mean, I'm sure if you just Google something like, if you just search like factorize large number, then you're going to come across FactorDB at some point. But also one other interesting calculator I found is Alpatron, which is this online calculator for you. Now, it's not like a giant database. It just calculates things like visibly for you using JavaScript and stuff. But it's very efficient, and sometimes you might get a number that's small enough to be factored, but just too large for FactorDB to automatically know. And so running a calculator like this is also quite good sometimes. Any other questions?
Yeah, from keys you've seen in like capture the flags, what kind of size does FactorDB in terms of bytes normally support up to? Like obviously you can't just chuck in a 4096 RSA key and expect it to chuck them out, but what kind of how high have you seen it go in terms of what it can factor?
Yeah, well, generally speaking, I think usually it's in powers of 2. I think, like for example, 256 is the, what do you think? Well, it really depends on the number. If you've got a modulus that's calculated perfectly and you've made no mistakes and you've just got to do a sheer brute force, then I think 512 bits is the, like 512 bits is quite a bit, but it's still doable, although it would take a couple of hours, or I think someone said like a couple of months on an average computer, but it's, I don't know. But that being said, this number here that FactorDB just calculated was 1024 bits, which should be large. But the issue is because it's consisted of lots of small factors instead of 2 large ones, it can be calculated very easily. And once again, even if you've got an absurdly large modulus, if the number was generated badly or something else, then there are other ways to factor it. Because it's very rare that a competition will ask you to do a pure brute force and just, you know, rent some giant server cluster over in India or something. Any other questions?
The guy's just paying the bill for you, I guess.
Sorry?
I guess in that case, the CTF prize would just be paying for your server bills.
Yeah, no, you wouldn't hope that. Although I have seen CTFs where they've asked you to like run, you know, hashcat and stuff. And I was actually talking to this other guy a while ago where he said he had this giant rig with like 8 different GTX 1080s that he was using to brute force some challenge, and it didn't look efficient. Any other questions? I might wrap it up there if there are no other questions. All right, I might call it here then. Thanks everyone that's done.